Hi there, my name is Eudes Naziazeno. I'm a visiting scholar here at UC Berkeley, and today I'm going to talk about the cubic equation. So it's a polynomial equation with the coefficients in real numbers such that the a is different from 0. And we're going to do this by doing some reductions along this class, right? The first one, since a is different from 0, we can put this like this and doing some, well, over a, b, and c, and then using that the real numbers are an integral is an integral domain to say that this has to be 0. So the first reduction is, well, we can admit that the polynomial is monic. The first coefficient is 0, right? So this is the first reduction. The second one is going to be, well, we can get rid of this coefficient here in such a way that the polynomial doesn't have a quadratic part. So for this, we just say that, well, for example, y is x minus something, and after this we can adjust this k in order to get rid of this part, right? So this is this was the first reduction, like first reduction, and this is the second reduction, right? So coming back to here, we can change this to y plus k cube plus a y plus k square plus b y plus k plus c equals 0, and then, well, just applying the normal identities, we can say that this is k square y plus q cube plus a y square plus 2ak y plus ak square plus b y plus bq. This doesn't matter that much, equals 0, right? This part doesn't matter that much. The point is that we can arrange these two here and ask this for b 0, right? So 3k plus a has to be 0. So this implies that we can choose k to be minus a over 3. So in this part here, if we just change to x minus a over 3, then when we are in this part, actually this cancels with this, and then it's going to be 0, the quadratic part, right? So we may assume that we can reduce the cubic to this form. And then you can ask, well, what are these coefficients p and q? Well, it's just the amount of coefficients that you combine in each power of y, right? And put together as p and put together as q, right? So this is the reduced cubic. Okay, now we are going to work on this reduced cubic, right? Okay, so remember that we did these reductions. So if we have a solution for this reduced cubic, we can go backwards until reaching the solution of the general equation, right? We're gonna apply a technique that was first introduced with a minus, but for the sake of the easing the solution, easing the formulas, the approach, we are going to consider x as the sum of u and v, right? We are separating this x as the sum of two variables, and well, let's see what happens. So x cubed is going to be u plus v cubed. Then, well, we know that this is u cubed plus 3u square v plus 3uv square plus v cubed, right? But well, this is x cubed by definition. Here we can put this together and say that, well, this is u plus v, and then this is u cubed plus v cubed, right? Well, by definition, this is x. So we can put this on the other side to conclude that x cubed minus 3uv x minus u cubed plus v cubed equals 0, right? Okay, this is very close to the equation that we have here in general. So we want this to be P and want this to be Q. And if we can solve this, right, we can come back and solve this one. So from this equation, we are asking that u cubed plus v cubed equals minus q, and uv equals p over minus p over 3, right? Okay, so now in order to go to a easier equation, we are going to take the cubic power of these two guys. And then what we have here? Well, recall that to solve the quadratic formula, the quadratic equation, is the same as find two real numbers in such a way that the sum and the product are the coefficients of the quadratic formula. So when we take the third power of this, we get that u cubed plus v cubed equals minus q, and u cubed v cubed is minus p cubed over 27, right? So we know the sum and the product of these two guys, right? So it's the same, this is the same as saying that u cubed and v cubed are the solutions of the quadratic equation t squared plus qt minus p cubed over 27 equals 0, right? Because in general, this is minus the sum of the two solutions, and this is the product of the two solutions of the equation, right? But the discriminant here, the discriminant is q squared minus 4 times this, so it's 4p cubed over 27. That makes the general solution to be minus q plus minus q squared plus 4p cubed over 27 over what? Over 2, right? So one of these is u cubed, and the other one is v cubed. So now we just have three cases. Well, both of them are real numbers or not. Okay? So, for now, well, u cube and v cube are this. U cube is, for example, the first one, plus q squared plus 4p cubed over 27 over 2, and v is minus q minus square root of q squared plus 4p cubed over 27 over 2, right? Okay, then from this equation over the complex numbers, these have three solutions, right? Well, the first solution is when this is real number and this is real number, right? First solution, u is the cubic root of minus q plus q squared plus 4p3 over 27 over 2, and v is the cubic root of minus q minus square root of q squared plus 4p cubed over 27, everything over 2. Okay? So, well, since x u plus v, then one solution can be the sum of u and v, simply. Right? So, I don't need these anymore, just for the rest of the solutions to have the other ones. Okay? So first solution can be, the first solution, x is the sum of these two real numbers. If it's real numbers, obviously, right? Over 27, over 2, plus the cubic root of minus q squared plus 4p cubed over 27 over 2, Okay? But this is just one possibility. When you have cubic roots in the complex numbers, maybe you can be facing the case when you take a cubic root of 1, right? And then the solutions for this first equation, u cubed like this, could be, for example, x could be this amount times this cubic root plus the square over 27, or the same but the other cubic root of 1, or and the same amount here. I will not repeat because it's the same here. Okay? And also for the, oh, I'm sorry, not x, u, right? And also for v is the same. V not only can be this number, but also can be the product of this with alpha or alpha squared. That is the other solutions for this in complex numbers. So V could be alpha this, well, again, these 3 dots here is this this number inside here, right? I'm not repeating. Or alpha square, square root of cubic root of minus q plus this. So, what other roots we could have from that? Well, let's remember the equations. U cubed plus v cubed equals, has to be in Q, or in R, I'm sorry, in R, and also U cubed times V cubed has to be, sorry, U times V also is in the reals, right? So if we choose these to be part of the solution, then necessarily the V that you choose is this one, because the product has to be in the reals. So you have one alpha here and alpha square here, and when you have the product, for sure it is in R, right? And analogously, if you have this to be U, then you have to choose this first option of V for the same reason. So these are the 3 possible solutions for the reduced cubic that we took from the general case, right? So this is one solution. The second solution is this U plus this V, and the third one is this U plus this V. Okay? Thank you very much.